And welcome back. I know I went a little bit long in my first segment, but I'd like to go a little bit further now and say that when we get to the atomic level, when we talk about chemistry, two things we want to know. One is that the electron has a charge, and that charge is actually measured directly by a scientist named Robert Millikan in a fairly famous oil drop experiment. And that charge works out to be negative 1.6 times 10 to the negative 19 coulombs. And obviously, we could say the charge on a proton would be positive that, same number. If we had something like a magnesium ion with a charge of +2, well, +2 what? The charge on the magnesium ion would be twice the charge on the proton, because remember, a magnesium ion would consist of 12 protons, only 10 electrons, because it belongs to, and some number of neutrons that we don't particularly care about right now, unless we talk about the mass. So the charge on the magnesium ion would be positive 3.2 times 10 to the negative 19 coulombs. And since our formula involves a force and then a constant, a distance, and two charges, anytime we are able to figure out or given in a problem all but one of those values, you should be able to use a little bit of algebra and calculate the others. The other thing I want to mention before we go on and talk about some experimentation is that this is certainly a appropriate expression of Coulomb's law, but force is not the most convenient thing to measure in chemistry, because first of all, it's a vector, so it gets complicated when you have to add them, or combine them, I should say. And it's much more relevant for chemists to talk about the energy of interaction. So those of you who might be in calculus might know that the energy can be derived from the force by integrating from some position 1, and if you're not in calculus, don't worry about it, to position 2, the force times the change. So those of you who are in calculus might appreciate that. But this generates another formula that says U, and for reasons I don't know, we use a simple U to talk about the electrical energy, the internal energy. I don't know why they call it internal energy either, because there really is no external energy. But the U equals that same constant K times the product of the charges over the distance, but this time only to the first power, so there's no square there, and we wouldn't normally write that. And the unit here is going to give us joules, because I'm going to have my newtons times meters, which is a joule. And so this is really the form that you are going to find most useful for answering AP chemistry questions. You'll never have to put in numbers, but you should understand that the energy will be negative when the charges are of opposite signs, will be positive when my two charges are of the same sign, since K and D are always going to be positive numbers, that the bigger the charges, the greater the magnitude of U. The further apart they are, or the greater the distance, the smaller the magnitude of U. So often you'll be asked to compare energies between different particles, and this is really the form that's going to be more useful. And we'll let you work out some problems on your own in just a few minutes, but I want to pause here and take one more video to kind of demonstrate Coulomb's law and charge.